Ready. Now, chapter 5, side problems, solution session, page 80. Let's take a look at this, try this problem.
Okay, so this one involves a rhombus inside of a triangle. And I think there's two things important about a rhombus. And that is that it's a parallelogram, but also all of its sides are equal. So I'm going to mark all of these as X. And I'm also going to keep similar triangles in mind because I can see that AB is 12, AC is 10, and FE is parallel to AD, and DE is parallel to AF, which means that DBE and FEC, they're both similar to ABC, right? So we can use similar triangles. We can pick either one. I'm just going to pick DBE. So we pick DBE and we compare it to the BAC.
So
And
you are making a parallel small triangle to the large.
yeah.
Great.
So BD is equal to 12 minus X. So we're going to do 12 minus X over X. And that ratio is equal to BA over AC, which is 12 over 10. So if we cross multiply, we get that. X is equal to 120 over 22.
Then we can go lowest term. What will be the lowest term?
The lowest terms, yeah. 60 over 11.
60 over 11. That is one side of the rhombus. That's good. Now let's move to one well-known theorem about parallelogram and bow tie. So a squared equal to b times b plus c. Let's try to understand proof of this connection. So this formula.
Yes. So bow tie is very important because we see we have a parallelogram, which means that these two are parallel and these two are parallel, which hints at using these two triangles for bow tie and also using these two triangles for bow tie.
Mm-hmm.
Right. Yes. So first, let's focus on the red triangles. We know that this is BK and this is AK because we both scaled them up by some amount in order to keep the ratio the same.
Mm-hmm.
And now what we can say is we compare the orange triangles and we have that BK over A, right? BK over A is equal to AK over B plus C.
So
And
A, this is A, right? A over
A over BK is equal to AK over B plus C. And now we can divide by K on each side and cross multiply and we get the theorem.
Wow. We used two bow tie triangles and we got this nice connection.
Yeah.
So how do we kind of memorize this one? A squared equal to b times the whole b plus c, right? Okay.
Yeah.
Let's see. And then that will lead us to previous problem, Andrew.
Yeah. The previous problem on page 83.
Mhm.
So we can do it the exact same way. We can say 2K, that's 4K, right? And then we do similar.
Or using this,
Which means
or
that X would be equal to 6. Or if you can memorize the formula, we have that 4 squared is equal to 2 times 2 plus X. And solving it this way, we also get X is equal to 6.
that is good application of this formula. We got these both.
Yes.
Now we are moving to page 85, chapter 5, try this site problem.
Yeah, so this one is more of triangle congruence than triangle similarity. So we have A, B, C. We have a point D on AC such that DBC is 20, like that. And we have a point E on AB such that EA is equal to DC. So we have these two are equal. And what we're going to be doing is we're going to be using the fact that it's equilateral, which means AC, so AC, and BC are equal. And we have that BCD, that's 60 degrees, and BAC, that's also 60 degrees. So now we're just going to use like SAS congruence, very simple. And we have EAC is congruent to DCB, which means that this angle here, DBC, which is equal to 20 degrees, it also applies to angle ECA. So this angle, ECA, is also 20 degrees. And now we have that that's 60, that's 20, which means the measure of angle AEC is 100.
Andrew, can you one more time write here what two triangles did you find they are congruent?
Yeah, it's important you get the order right.
Yep.
DBC, triangle DBC, and triangle ECA.
ECA. They are identical, right? What we call the congruent.
Yeah, they're congruent because we found two sides are congruent and the angle between them.
What do we call side?
Side angle side.
Side congruence.
Yes.
Which is similarity ratio is 1, right?
Yeah, similarity ratio 1. I mean, since it's dealing with angles, whether or not the similarity ratio was 1 wouldn't matter, but.
Good. Perfect. We got this one.
Yes.
Now,
we have this.
Page 86, another similarity types of problem. Let's see how we use, what kind of similarity are we going to use?
Yeah. So let's focus on this angle here, BCD. And now we realize that ACB is similar to BCD. And that now it's just one ratio. So 6 plus X over 4. So ACB, we said, is similar to BCD, which means 4 over X. Right. So if this is
can you one more time write the letter and row?
Yeah.
For what?
Yeah. So this might be a little bit confusing.
Mhm.
So I'll draw the triangles separately. So here's that triangle, and I will take ACB and we'll kind of flip it like this.
Okay. Sounds good.
So we have this triangle, DCB, and we have ACB, right? And notice this is equal, equal, equal. And we have that this angle DBC, that's equal to angle BAC. So by AA similarity, these two triangles are similar, these two specifically. And now if we put in the lengths, DC is X, BC is 4, and AC is 6 plus X.
Great.
Now it's very clear that the ratios are 6 plus X to 4, and then 4 over X.
So 4 over X.
Yeah.
And plus X over 4. Now perfectly clear.
Now we can just cross multiply. And we do get a quadratic, but that's fine because
Can we? Okay, good. We
It's
can
very-
attempt always quadratic, but maybe we can guess possibilities.
yeah, factors. And whether or not you use the quadratic formula or like just simple like guessing and checking or like factoring, like the sum product thing, like this, doesn't matter. You'll end up with x plus 8 times x minus 2 is 0. And since x has to be positive, we know that x equals 2.
That's why we are looking for. Great.
Yeah.
Page 87, another side challenge problem. Let's see. I smell bow tie, Andrew.
Yeah.
What do you think? Let's see.
I also see bow tie. This one's actually nice because it combines bow tie and similar triangles. So let's look first at the similar triangles. So we have this triangle ADE and triangle ABC. And notice what this shows us is that the ratio of AE to AC is 1 to 3, right? So AE is X, and we know that EC right here, EC, that's 2X, because we know the ratio of AE to AC has to be 1 to 3, right? So now the second part is the bow tie. So these two triangles right here, marked in orange. So what we notice is that the ratio of EK to KC has to be 1 to 2, just like 6 to 12 is 1 to 2, which means we have to divide this 2x into 3 parts. So this is 2x over 3, and this contains 2 of the 3 parts. So 2x times 2 over 3, which is 4x over 3. So everything works out. We have the bow tie works and the similar triangles, and the ratio of AE to KC is just x over 4x over 3, which is equal to 3/4.
Great. 3 over 4.
Yeah.
What if, Andrew, what if, okay, let's clear this one. What about the second? If you were to, Andrew, start with first these two length, can you do
Yeah.
one, please?
So, I mean, that would also result in a fraction.
Okay.
You can start from this. You can say K, 2K, and then we have AE has to be 1/3 of the whole thing, which means it's 1/2 of 3K. So we have 3K over 2 for AE. And when we take the ratio this time, we'll end up with 3 over 4 again.
Okay. Now that's both solutions are clear.
Yes. So this is a median problem.
Do we have a special name for intersection of these three medians?
Called the centroid, and it is the balancing point of the triangle, and this fact that the centroid is like the balancing point kind of relates to something called mass points, but you don't need that to prove this.
Mhm.
So if
So
you don't,
you are going to use proof without using mass point. Okay.
yeah, if you know mass points, you probably
Mhm.
know that this is really easy to prove.
Let's see. Let's suppose we don't know mass point and how.
Yeah. So we have this triangle, and what you can think is we have these three medians, and we need to prove that they concur in the same point, and that the partitions is 2 to 1. So this is 2 to 1. Yeah, so the first thing that you can do to show that it is a ratio of 2 to 1 is that these are equivalent.
Andrew, do you think that if we connect E and F, would it be helpful?
Yes, that is the midline.
Mhm.
Yeah, the midline. And that divides it in a 1 to 2 ratio. So call this, we can call this 3K, and like this length 3K.
Do you also smell bow tie, Andrew?
Yes, bow tie, I was about to mention. So EF, this is equal to twice EF, so CB. And that means this is 2K, and this is K. And now we can see that it's divided into a ratio of 2 to 1. So each of the medians in the intersection point is divided into a ratio of 2 to 1. And now we can show they all concur at one point by using the fact that they're divided in a ratio of 2 to 1. So can you erase your line?
Mm-hmm.
Yeah. So if we erase all this, so we have these two lines, and we know they're divided into ratios of 2 to 1. And when we draw a line through their intersection point, we know that there's only one median in the triangle, right? So if we draw a line that passes through the point, and we call this point here D, then we can draw in this line, and basically we can do it in reverse. So we have xk, we know this is A and this is 2A, and because it's a midline, this is 3A, which basically proves that the line that passes through this point of intersection of the other two medians, that line is also a median, which shows that they all three intersect in the same point, because there's only one median corresponding to each side.
Andrew, can you also just quickly show why using mass point? Just quickly.
Yes, mass point. So mass points makes it really fast. So we have 1, 1, 1, right? So we give each of them, say, a mass of 1 because they're each about a midpoint. And then the midpoints have masses of 2, which means that the center point, no matter where you count it from, so like let's say we intersect these two, it makes 3. So all 3 of them agree that it has a mass of 3, which means they all sort of concur, which is kind of why you call it a point of concurrency. Yeah, so since they all agree that it's a mass of 3, that means that they intersect at that point. And we have that because this mass is 2 and that mass is 1, and corresponding around the triangle, that means this is like 2A, A, 2B, B, and C and 2C because of the masses. So for example, 2, 1, meaning that this is C and 2C.
Great. Now that is our chapter 5 side problem from page 89.
Yes.
What
So,
theorem should we use this case, this problem, Andrew?
yeah.
Always that's very useful for theorem are you going to remind us.
Yeah. So I see that there's an altitude drawn in a triangle.
Mhm.
And I see that we know one of the sides. And what comes to mind for this is like this.
Oh, I can draw here and then you can show here.
Yeah, sure. Okay.
Let's say, let's draw here. This is the height, suppose.
Yes.
This one.
So let's say that this is equal
H.
to A, B, and C.
Mhm.
We have that A squared
Oh,
is equal to, yeah?
Yeah. You
Is
put
equal to B,
that's fine. Mhm.
B times B plus C.
Mhm. Then H, what about H?
Yeah, so we also have H squared is equal to B times C, but because we don't know the height and we don't know both of these BF and FD, we can't use that one. So
This case, A squared B times B will be useful.
yeah,
So where do we start?
so we can start right here, right? So we have that 6 is equal to 4 times, well,
6
6 squared, 6
squared.
squared is equal to 4 times 4 plus 2 plus BE. So it's 6 plus BE, which means we have 36 is equal to 24 plus 4 times BE. And if we solve this equation, we get that BE is equal to 3.
Perfect. Now, what do? We will focus on green triangle, right?
Yes. So in this one, let's focus on AB since that's what it's asking for. Let's call it X. We have that X squared is equal to 3 times 3 plus 2 plus 4, which is 9. So that means X is equal to the square root of 27. So AB is equal to 3 times the square root of 3.
So that conclude our chapter 5 side